So today is our last method to learn for finding volumes of solids, and it's called the shell method. It's similar to the disk method, similar-ish, in that we're working with the shell method when we're doing volumes of revolution. So I wanted to review really quick the disk method before we talked about the shell method. So when we say cylindrical shells, this one's pretty hard to visualize. I mean, they're all kind of hard to visualize, especially if you don't like three-dimensional visualizations. I've had practice, because I've been doing this for years and years, so for me it's a lot easier now. But I remember when I first started, I was like, what are they talking about? I have no idea what that's going to look like. So it still will be hard to visualize, but we can still actually do the formulas, even if we can't visualize what it's going to look like. But when we did volumes of revolution, what was our final formula to find the volume of something revolved?
Integral from A to B pi times the function squared.
Yes.
So if you have f of x minus g of x, are they both squared?
Yes. So when we do that, since we have the pi out front, so if we do have a hole, some empty space, sometimes we have to minus our lower function. And this works if we're around the x-axis. So we do sometimes have to shift our function up or down so we get to the x-axis when we're actually revolving around the x-axis. So when we worked with that, we would take a shape and we would actually revolve it around. Maybe. Come on. We worked earlier.
How is she going to do it? I don't know. I'm not this part.
There we go. So we actually revolve it around the x-axis.
Oh, it's supposed to be revolving.
Yes. And we took that and we cut them into circular pieces. It's like we took that, made it out of Play-Doh, and just cut the Play-Doh into slices. And that's how we figured out we were using pi r squared, because area of the circle is pi r squared. So,
That's what I said.
It kind of keeps
Kinda
changing.
does.
Sometimes it fills the whole thing, and sometimes it doesn't.
so with cylindrical shells, sorry, this one just runs automatically, so it's not at the beginning. Come on. With cylindrical shells,
Oh,
we're
you
taking
broke
a
it.
region still, we're cutting it into sections, just like we sliced our object into circular pieces. And the cylindrical shells works best if we're rotating around the y-axis. So we're taking actually a cylinder. We're taking a shape, and it's like we're, you know, like an apple core?
Yeah.
Taking out a chunk of it. It's that same idea. We're taking out a cylindrical chunk, and we're trying to find the area of that cylindrical chunk.
That you're taking out.
Yes.
So that hole in the middle.
This, yeah, cylindrical piece. We're trying to find the area of that. So, what shape does that piece make? A tube, a cylinder. Okay. Well, if we have a cylinder, maybe. I need a non-cut into piece. So I'm gonna go down below so it doesn't keep rotating. That is a mistype.
How is 25x?
It should have been 2. But I
Oh.
just typed it in wrong and I didn't notice till now. If we have a cylinder and we want to find the area of this cylinder, We didn't say find the volume of the cylinder, the area. If we add up all the areas of our cylinders, then we get the volume, and we add them up through integration. So how do we find the area of a cylinder? What shape, if I take my cylinder, I cut, and I flatten it out, it's a rectangle. So what's the area of this rectangle? Close.
Not diameter, circumference.
Circumference times height. The outside of the circle times the height. So circumference times height. So we have 2 pi r is our circumference times the height of our cylinder. So that's where the 2 pi r came from. That was circumference. Times height. And then if we add all the various areas up, we get the volume. Just like we've been doing with all our different shapes. When we added all the areas of the different cross sections up, we get volume. When we added all the different slices up from our volume of revolution, we get volume. So I'm going to rewrite this just so you can see it nicely. 2 pi, since I had a mistype typo.
I know, right? Because I'm like, well, it looks like that. Why does mine never be like that?
Oh, because of the calligraphy pen. Okay, so let's try an example. We've been doing a lot of volumes, so it'll be very similar. We'll be looking for some of the same things as we do our volumes. So let's suppose we have a region bounded by x minus x to the third and y equals 0. So it's bounded by those two functions. And it's revolved around x equals 0 to form a solid. So what is our axis of revolution in this case? What are we revolving around? It's the y-axis. It's x equals 0, which is really the y-axis. And we want to find the volume. So we need two things. We need the radius of our cylinder, and we need the height of our cylinder. So when we were working with washers, the radius was always basically the function. That is not going to be the case with cylinders, with shells. So if we graph this function, it looks, the piece we're looking at looks kind of like a flattened dish parabola. And I didn't draw any of the rest because that's the part that's enclosed by the function and the y-axis. So there's our function. And we always find from our axis of revolution and we take a random partition. Any section, just like we had that section on the applet that was going around and making a cylinder. We take a random section so we can decide what's the height of this random section and what's the radius, what's the distance to that section from the axis of revolution. So what will the height of this section be, this partition? The y value on the function. No matter where I took this partition, it only ever goes up to the function. So the height in this case is the function itself. But the radius is the distance from the axis of revolution to our partition, to our piece that we're trying to check what the height and radius would be.
So the radius is from that part to the y-axis in this case?
Yes. So we have to figure out what is that distance. Let's put it down here instead. If we go from the y-axis to a random spot, what do we draw? it's the x value. Our radius is usually our x value. Our height is usually our y value. So our x value here is x. We didn't say we want it specifically at 5 or whatever. We just said an x value and a y value. Well, there's a random x value that goes with our random partition. But the y value is determined by the function itself. So our volume would be 2 pi. And then we need bounds. How am I going to figure out the bounds for this? How do I know where to start and to where to finish?
Would it be the it's radius minus and
Usually where we start and where we finish is just where the shape starts and where the shape finishes.
oh, so it would be positive.
So where
So
do we
0 to
start?
x.
0 to whatever this is. That is a specific point. We know it ends at a specific point. How do I find that specific ending point?
It's a 0.
It's a 0. So if I set the function equal to 0, how am I going to solve that?
Or you put in
How am I going to solve it by hand? Factoring.
Try.
Pretty much every time you're equal to 0, you're probably going to have to factor. So I can factor out an x. And then what type of factoring would I use for that? Difference of squares. So we have x times 1 minus x times 1 plus x. So that means we have 3 possibilities.
x equals 0.
X equals 0.
X equals 1. Or x equals negative.
Correct. X equals 0. X equals 1. X equals negative 1. Now one of those is completely useless to us. Which one doesn't matter at all?
1.
Negative 1. It's not on our picture at all. But we do need to go from 0 to 1. And then we just do our radius times our height. What was our radius?
X.
X. What was our height? F of x, which in this case was the function x minus x to the third. And then we integrate and use the fundamental theorem of calculus. So I'm going to distribute the x in to make it easier for our integration. We get x squared minus x to the fourth. Now I can actually integrate using anti-power rule. So what will my integral be?
Would be 1/3.
1/3 x cubed or x cubed divided by 3, same thing.
That's what I do. And 1/5 x to the third. This is represented from phone and like,
Evaluated from 0 to 1. Then we apply fundamental theorem of calculus. We plug in 1, so that doesn't change anything. 1/3 minus 1/5. If we plug in 0, we don't get anything, so we can leave off the minus 0 part. If you want to plug it in, go right ahead, because sometimes it is necessary. If that was a trig function, 0 might not actually come out as 0 when you plug it in. Or if it was like e to the 2x, e to the 0 would be 1. So sometimes we do have to plug it in, but when it's a polynomial, it just comes out 0. So we would subtract 2 over 15. So we get 2 pi times 2 over 15. All I did was 1 times 5 is 5, 3 times 1 is 3, 5 minus 3 is 2, 3 times 5 is 15. So I kind of shorthanded my fraction and didn't write it all the way out. So we multiply 2 pi times 2 over 15, and we get 4 pi over 15. I didn't have to find this area using shelf. I could have used disk method, but if we were going to use disk method, does everyone have this before I scroll back up? If I were going to use disk method on this function, we know it revolved around the y-axis instead of the x-axis, which means our radius is actually in terms of y. When we found our circles, we had to go from the axis of revolution to the function. So we'd have to say x equals instead of y equals, which actually in this case would be impossible. I didn't think about that. Just most shapes you can use both, but I can't get this to say x equals.
She's not that good.
It's impossible.
Or you.
Or everyone. So I want you guys to try one, and then we're going to do one where our axis of revolution isn't the y-axis anymore. So if we draw our graph, we said just from 0 to 1, we take a random partition. What's the height of that random partition? X, because the function was y equals x. And what's the distance from our axis of revolution? It's also x. So you ended up with 2 pi integral, they told us the bounds, we didn't have to find them this time, 0 to 1, x times x dx. Simplify and integrate, if you do all that, you get 2 pi over 3.
How do you know the radius is x?
So the distance from the y-axis to any random positive point is x. The
Right.
distance from the y-axis to any random,
Negative.
if I was going up, the distance from the x-axis to any random point is y.
And then that'd be negative.
And that's very random. It could be down here, and that's negative y.
So most of the time it will be x for the distance,
Yes.
but the function will change.
Yes.
Okay.
But the height will change depending on the function. Unless we do something a little bit different. You don't cover this.
No.
So let's say our region is bounded by, I forgot to superscript that, x cubed plus x plus 1. And then I just had a random L. Wow, my typing skills were fantastic today.
That's sarcasm.
Yes, yes it was.
So when are your dividers?
Y equals 1 and x equals 1, and it's rotated around the line x equals 2. So now we're no longer rotating around the y-axis, we're rotating around a different vertical line. Again, the shell method is usually better when we're rotating around a vertical line instead of a horizontal line. Disk is usually better when we're rotating around a horizontal line. I say usually because there are instances where you have to do one way, and you couldn't do both ways. So if we draw our axes, we know the easy ones, y equals 1. I'm going to make this kind of wider since we're taking such a small space. I'm going to say this is 1, this is negative 1. So we know the line y equals 1, horizontal line, the line x equals 1, vertical line. and then x cubed plus x plus 1. What will that look like just for that tiny space? Let's plug it into our calculator to see. We don't really care about the entire graph. We just care about that little section that we're working with. If you want to clear stuff out, you can just hit dock the dock button on the right now. You don't have to hold dock down. So we're kind of focusing what's going on at 1. The x cubed plus x plus 1. We're plugging that into C. And when we plug it in, I believe it crosses through 1, or 0, 1, right? Yeah. So at 1, it's where it's crossing, kind of goes up like that-ish. So our shape that we are working with is just this almost triangular piece right here. That's our shape. But now we're rotating that shape around the line x equals 2. This is our axis of revolution. It's x equals 2. So we still need to do the general idea of, let's find a random partition. Here's a random partition. So I need to find two things. I need to find the height of this random partition, and I need to find the distance from the axis of revolution to that random partition. The height is a little bit easier, so let's start with the height of the random partition. So what's our height normally of the random partition? It's normally the y value. It's normally the function. But the y value in this case, different color. The y value in this case would take us from, why did you not let me pick a random color? Come on. There we go. The y value in this case takes us from the x-axis all the way to the function. That has a whole lot of extra space. How am I going to get rid of that extra space that's not actually used in the height? Minus 1, we take it away. We don't want all of this stuff. Well, all of that stuff is a distance of 1, so we take it away. So our height is x cubed plus x plus 1 minus 1, because we're trying to take that empty space out of our equation. So then we need our radius. Our radius is the distance from the axis of revolution to our partition. Again though, what's normally our radius?
X.
Normally it's x, but when we have x, x is the distance from the y-axis to our partition. That's the wrong direction. So we take the entire length, and now we want to take away the x piece. The x piece is actually what we want to be getting rid of.
So it's 2 minus x.
So it's 2 minus x. And once we figure that out, then it's just plug it into the formula again. Volume is 2 pi. Sorry, I almost forgot to write the 2 pi, and that's why it's squashed. Integral. Now, where are our bounds?
0 to 1.
Okay. 0 to 1. You might think, I might sometimes think 0 to 2. Why would I maybe have thought 0 to 2?
Because that's where that is.
That's where we're rotating at, but there's no function there. The integral is actually adding up the pieces of the function, So why would we integrate when there's no function from 1 to 2? So we just go from 0 to 1. We take our radius times our height. This time, I am going to cancel out the 1s. 1 minus 1 is 0, so I'm not going to write that in. This time, just use your calculator. I'm not going to make you FOIL that out and integrate by hand. Maybe I should make you integrate it by hand then.
About 29 pi over
29 pi over 15. Is anyone confirmed that? Yep. We have 2. Anyone else get the same thing? Okay.
Yes.
Okay. 29 pi over 15 is our final answer then. So you are going to have about half an hour for your homework. That means you should get the majority of it done in class. Maybe not finish it completely.
Majority of it, how big is this assignment?
You might finish. I just hate saying you're going to finish and then someone doesn't finish and then they feel bad that they didn't finish. So I use the word majority. Try and be a little
And
PC
someone,
here.
she used the word someone too.
But you also broke the promise
What promise?
that you wouldn't tell